Hello everyone, this is Group 21 and today we're going to talk about learning to stand up using hierarchical reinforcement learning by Kenji Doya and Yoon Morimoto. The presentation starts off with the introduction, providing the motivation behind hierarchical reinforcement learning, followed by the HRL method being followed in this paper. Then we're going to delve into some of the simulations performed in the paper and our take on those simulations, followed up by some of the discussion points and finally the conclusion. Now, why do we need hierarchical reinforcement learning? One of the main issues with the standard RL technique is scalability. For a robot having multiple motors, the state space representation explodes exponentially with the increase in the number of motors. This means that the solution has to be searched in the entire space rather than a small hyperplane within that large space. This is inefficient. Another problem is overfitting. This means that when the agents are trained in a certain complex environment, they don't generalize well to other similar new environments. This reduces the adaptability of the reinforcement learning technique. So what is hierarchical reinforcement learning? HRL uses the divide and rule strategy to decompose an RL problem into a hierarchy of upper and lower levels. The upper level is typically low dimensional, where a large task is discretized into chunks of smaller tasks, which are then fed to the lower level. The lower level is high dimensional and continuous. And the advantage of such a setup is that it reduces the complexity of the problem. For example, if one has to learn the task of cooking a complicated dish, it can be further subdivided into first cooking the meat and then cutting vegetables and adding spices, etc. If the act of cutting two vegetables are the same, then the policy learned on cutting one vegetable can be used on the other. This increases the modularity. Now let's look at some of the popular HRL techniques. Feudal learning involves splitting a task into multiple layers, where each layer is discretized into grids having different resolutions. The layers represent managers who are assigned tasks from managers above and in turn pass on subtasks to the managers below. It employs bidirectional information hiding, where managers are only aware of the state of the system on its level and have no knowledge about the orders from two levels above nor actions taken 2 steps below. It is this method that reduces the state space of the system, promoting early exploration and faster convergence. Hierarchies of machines consists of non-deterministic finite state machines, which at any point are in one of the 4 states: action, call, choice, and stop state. Here, actions aren't learned on every state, rather decisions are made and eventually learned only when the agent enters the choice state. This reduced state space enables faster learning of policies for POMDPs. The max-Q method can be explained by the tree-like structure consisting of context-independent max nodes and context-dependent Q nodes. In the figure, the context-independent navigate function is being used by both the get and put functions, thereby improving the reusability and sharing aspects of these subtasks. This type of formulation entails recursive optimality, that is, a policy that is locally optimal for each subtask, which restricts the type of problems that it can solve.
In this slide, we are going to see about the upper level part of the hierarchical reinforcement learning. The upper level uses Q-lambda learning to learn the low-dimensional state space for the given robot. What exactly is Q-lambda learning? It is nothing but the combination of Q-learning and TD-lambda learning, where the update step of Q-learning and the lambda parameter from the TD-lambda learning is used. The actions in the upper level are based on the Boltzmann distribution, where for a given state, a set of possible actions are drawn from the distribution. This Q-lambda learning uses another interesting parameter called eligibility traces to accelerate the convergence. So what exactly this eligibility trace does? They keep track of the actions that happen in the previous timestamps and weighs them accordingly, which are eligible for the future learning process. In the next slide, we are going to see about the equations that are used in the Q lambda learning. In this slide, we are going to see about the equations used in the Q lambda learning. The first equation here is a state value function, which gives the information about the possible future rewards you may get for being in a given state S. The second one is the prediction error. The prediction error is used to improve the prediction accuracy for the future rewards. So there are two equations in the prediction error. One is for the current state, that is S is equal to Sk, and the other one is for the remaining states. The R of t in the prediction error denotes the rewards obtained at time t, and gamma is nothing but the discount factor. The third one is the eligibility trace. So similarly to the in prediction error, there are two equations. One is for the current state and the other one is for the remaining states. The lambda in the eligibility trace takes values between 0 and 1, which is known as trace decay parameter. The last equation denotes the final update step of the Q value function. So the Q value function is updated based on the prediction error, eligibility trace, along with the learning rate alpha.
The next level in the hierarchical reinforcement learning is the lower level. The main goal of the lower level is to attain the state specified by the upper level. The authors have implemented actor critique in the lower level. So what is actor critique? Let us take an example of a child playing in a playground. The child is the actor in our case. All the actions taken by the child are not appreciated by the parent. The parent plays the role of a critic by having a watch on the actions of the child and penalizes undesirable actions. The same applies in reinforcement learning, where the actions of the actor is penalized by the critic. In a natural actor critic algorithm, the actions taken are undesirable and unstable. So the authors have fused actor critic with TD lambda to penalize the visited states using eligibility traces, which was discussed earlier in the upper level. In contrast to Q learning, the actor critic learns the value functions and the actions control sequences separately. The actor learns the control sequences and the critic learns the value functions. The output of the actor and critic are based on neural network, where the weights of the neural network is updated using eligibility traces. The rewards of the lower level are based on the current posture of the robot and the desired posture. The authors simulate the 3-link 2-joint robot to validate the learning speed and also to validate the number of trials taken by the algorithm to learn the standard behavior. The upper level operates in low dimension, having the state of joint angles, and the lower level operates in high dimensions, having the state of joint angles and their corresponding joint angular velocities. There are limits set to each joint in the upper and the lower level. For example, theta 1 has a limit minus 150 to 0 in upper level and minus 150 to 150 in the lower level, because the learning of the control actions are in continuous state space in the lower level. In one of the simulations, the authors set the joint angle theta 2 to 0 by transforming the 3-link robot to a 2-link robot. As the upper level take discrete actions on the state to be achieved as a sub-goal, the joint angle theta 1 has different step sizes, namely 20 degrees, 30 degrees and 50 degrees for 3 different simulations. The robot learns to stand up in finite number of trials for step size of 20 degrees and 30 degrees, but fails for step size of 50 degrees. Why this behavior occurs? Let us discuss in the next slide. From the figure, we can see that for step size of 20 degrees and 30 degrees, the number of sub-goals learnt are higher than the number of sub-goals learnt with step size of 50 degrees for theta 1. A crucial sub-goal at minus 125 degree for theta 1 is not learned by the lower level and the standard behavior fails for theta 1 equal to 50 degrees, for step size of theta 1 being 50 degrees. But for other simulations where theta 1 being 25 degrees and theta 1 being 30 degrees as step sizes, the crucial sub-goals is learned and the trajectory is smooth. The crucial sub-goal is missed because of the limits in joint angles of theta 1. As I said in the previous slide, the joint angles for theta 1 is minus 150 to 0 in the upper level. So the two discrete actions it can take for the upper level are minus 50 and minus 100 degrees. As a sub-goal at theta 1 equal to minus 125 is not learned, the lower level needs to learn complex trajectories instead of a smooth trajectory. So there exists a certain range of step sizes for a successful standard behavior.
So in the discussion, I would like to talk about the advantages of hierarchical learning and the method used by the authors to implement the hierarchical learning. So talking about prior knowledge, the one of the main advantages here is the authors have used the prior knowledge in both the upper and lower layers, but how exactly have they used it is by first talking about the upper layer is the use of three state variables theta m, theta 1 and theta 2, and the action is defined here based on the formula u of t is equal to x of t minus 1 plus del x. So based on this formula, it is known that at any state x, the agent can choose one action with a probability p from a set containing of 27 actions based on the state variables, yes. And the prior knowledge to the lower layer is based on the linear dynamics of the servo and the joint angle constraints. So this is based on the practical constraints, the maximum angles the robot can reach, which is already known, so that can be given in the form of constraints for the lower level. On the other hand, it is to be noted that the authors have applied the hierarchical learning directly to a simulation rather than a real robot. This is due to the fact that a real robot has to have an intermediary goal or an initial start position based on a number of runs, because the real robots results vary for individual runs based on noise and aging. So using simulations makes this learning process faster, cheaper and safer. And it is also to be noted that the sub goals have been used from the simulations to the real robot. This reduces the search space of the robot, and it also makes the simulation much safer. So however, uh, it is difficult to simulate the actual dynamics of the real robot and its environment, and the sub goals might differ. So to conclude, we would like to point out the authors have used the accumulating traces in the update of eligibility traces. So we suggest the use of replacing trace, which will improve the convergence while retaining the recent heuristic and discarding the frequency. So the extent of prior knowledge in the upper level can also be reduced, where the robot can learn the set of available states and actions and also stand up from different orientations. That brings to the end of the presentation. Thank you for your time.